Now let's look at calculating probability using what we call complements. To find the probability that an event E will not happen, you take 1 minus the probability that E will happen. So this is because the probability of something happening plus the probability of it not happening, those are the only two options. It either does or does not happen. So when you add those together, you get 1. So if you ever want to find either or, you simply subtract the other one from 1, and then there you have it. This is just another way to calculate some probabilities. A lot of times it is easier, but not always. So we'll take a look. So it says we're going to take a number selected at random from the set of integers from 1 to 50 inclusive. Find the probability that the chosen number, and part A says, is not a perfect square. So in order to calculate this directly, we would have to count up all of the non-perfect square numbers between 1 and 50. But there are a lot of those. There are much fewer perfect squares. So I think this one would be easier done by a complement. So if I think of perfect squares between 1 and 50, we've got 1, 4, 9, 16, 25, 36, and 49. So there are 1, 2, 3, 4, 5, 6, 7. There are 7 perfect squares between 1 and 50. So if we want to find the probability of not picking a perfect square, we could use the complement rule. So we could say probability of not, I'm going to call it not a perfect square, not PS, is equal to 1 minus the probability that you do draw a perfect square. So 1 minus, out of these 50 numbers, 7 of them are perfect squares. So that would be 50 out of 50 minus 7 out of 50, which is 43 out of 50. So could we have calculated that up directly? Yes, of course we could have. We could have counted all of the non-perfect squares, but it was a lot easier to just subtract off the ones that are perfect squares because it was a smaller number to count up. Similarly, part B says, what's the probability that we do not choose a multiple of 7? So probability of not a multiple of 7, I'm going to write times 7 for that, can be equal to 1 minus the probability that it is a multiple of 7, because there are not that many multiples of 7 between 1 and 50. We can write them out. So let's see, there's 7, 14, 21, 28, 35, 42, and 49. So there are 1, 2, 3, 4, 5, 6, 7. That just randomly happened that both things, examples that were chosen here, had 7. So we're doing 1 minus 7 over 50 again, which we already know from the prior problem is 43 over 50. So the fact that those came out the same is just random. Okay, what about the probability that the number chosen is not larger than 45? So let's look at it the same way. Not larger than, so the probability of being not larger than 45 is equal to 1 minus the probability that it is larger than 45. So 1 minus how many over 50? Okay, so how many numbers are larger than 45? Remember, again, between 1 and 50 inclusive. So the first one would be 46, 47, 48, 49, and 50. So there are 5 of them. And again, that's 50 out of 50 minus 5 out of 50. So it's 45 out of 50, and that reduces to 9/10. Now, just as an example, could we have calculated that one directly? Probably, because of the way it's set up, it would have just been as easy to say, well, the probability of not being greater than 45, this is the same thing as saying being less than or equal to 45. That's just another way to say it. So maybe you could have just thought in your head, oh, well, there are 45 out of 50 values that are less than or equal to 45 and arrived at the same answer that way. So not everything that's written as kind of a complement setup has to be done that way 100%. Usually it's faster, but in this case, I'd say both of those are pretty much equally as quick. Okay, what is the probability that the number is not between 25 to 35 inclusive? I'm going to use the complement rule here. So the probability of being not between 25 less than or equal to x less than or equal to 35, right? Because inclusive means equal to here. So if we are not that, that would be 1 minus the probability that we actually are that we are between 25 and 35 inclusive. Now be very careful here. So if we're including the endpoints, we actually have 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 35. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different values that would apply there. So this is 1 minus 11 out of 50, or 50 out of 50 minus 11 out of 50. And that comes out to 39 out of 50. So it may seem very simple, and you may not want to write all of the numbers out that are included there, but you risk, which actually I made the mistake the very first time I did this, I just said there were 10 of them because I looked at 25 to 35 and I was like, oh, those are 10 apart. And I didn't take the time to write it out, and I made an error. There are 11 numbers that are counted there when you count in both of the endpoints. So just better safe than sorry to jot those down to make sure you get the right values.